Hello, pre-calculus students. Okay, sorry about the glare up here, but that just says Math 2412, pre-calculus, and of course the number one identity, which I don't need to tell you, cosine squared plus sine squared is equal to 1. We're going to use that in a minute. Along with the number two identity that the cosine of twice theta, which is cosine squared minus sine squared, is going to give us our last four identities, the two power reduction identities and the two half angle identities. I think we went over this in class, but I just want to have it all on the YouTube channel for somebody who maybe wasn't there. Okay, so the number one identity, cosine squared plus sine squared equal to 1, actually gets used in one of these two forms a lot in the calculus. Replacing the cosine squared with 1 minus the sine squared, or vice versa, replacing the sine squared with 1 minus the cosine squared. Both of those come from this, right? Just solve for the cosine squared by subtracting that, or solve for the sine squared by subtracting the cosine squared. So those are nice if you need to get out of an expression to get rid of all the cosine squareds. You can replace them with 1 and a minus sine squared, or vice versa. That kind of thinking happens when you're in Calc 2. But integrating sine squareds or cosine squareds is not so easy. So in fact, we do the following. We take that number two identity, the double angle identity for the cosine, which has a difference of cosine squareds and sine squareds. And for example, if you replace that cosine squared with a 1 minus sine squared, right, you get cosine twice theta is 1 minus 2 of the sine squareds. I'm doing a little algebra. And if you solve for that sine squared, you get the first power reduction formula, which is that the sine squared is equal to 1 minus the cosine of twice an angle all over 2. Why is that of any benefit? You don't really see the value of it until you get into that Calc 2 situation where you know how to integrate something that looks like that. That's the same thing as a half minus some constant times a cosine, which has different frequency. Integrating the right-hand side here is dead easy. Integrating the left-hand side is nigh impossible. So in fact, when you have square powers of the sine or the cosine, you often use these power reduction formulas to be able to go from a square to power of 1 of a trig function there. And that helps a lot. How do we get the cosine squared power reduction formula? Same trick. Go back up here, and instead of using cosine twice theta with a bunch of sine squareds, do a replacement. So you're dealing with cosine squared minus 1 minus cosine squared. Solve for the cosine squared, and look how you get these two power reduction identities that it just differ by one operation right there. Okay, so these are valuable and useful in a lot of exercises in Calc 2. Another thing that happens is if you apply the square root principle, which, let me talk about that square root principle a little bit, because you're going to need to use that again and again. Again, if you have the square root principle is this, that if you start off with some quantity squared is equal to a constant, okay, you can reduce the power on that to just x, as long as you remember to put on the other side plus or minus the square root of whatever that constant was, okay? That's applying the square root principle. And we're about to do a whole bunch of trig equations where we use this, and where if you don't use the square root principle, if instead you do something not good, like just take the square root of both sides, you're going to lose an infinite family of solutions in a trig equation if you don't apply the square root principle, okay? So this gets used a lot in the calculus and on up, and so you want to make sure that you're always doing this. You're never just taking the square root of both sides. And even though HISD sort of pushes that as if that's a viable thing, it's what you never want to do again, okay? Now you're in college, right? So you're going to apply that, and we're going to apply it here. So this sine squared becomes just the sine of theta here, and the right-hand side of that becomes plus or minus the square root of this. Now, why do you have to have this? Well, this is supposed to be an identity, true for any theta, right? And there's plenty of angles theta where the sine is a negative, right? If the angle terminates in quadrants, you should be able to answer this, quadrants 3 or 4, the sine has got to be negative. So that's why you have that. You can think of it as that's why you have to have the plus or minus there. So this identity works for all angles. So this, that gives us these formulas. Now, as far as these being useful to you when you're in the calculus, not so much. I mean, you wouldn't want to replace a nice pleasant sign with plus or minus the radical of this rational expression involving the cosine of twice the angle. No, you wouldn't want to do that. However, if you make a substitution, if you allow theta in here to be equal to alpha over 2, or for some angle alpha, notice that implies that twice theta in there is just alpha. If you do that, then you have something very useful, which is the half angle formula. Useful / just beautiful. Yeah, really? Something with fractions and negative signs and radical signs is beautiful. Well, it depends on what you do with it. So, sorry, I'm trying to get rid of glare on that bottom part of the screen, and I'm going to have to rotate this to make that happen. Okay, so for example, so we have some half angle identities for the sine and the cosine. First of all, notice that you really have to just memorize one of them and remember that this subtraction becomes, oops, an addition over there. Yeah, that was an addition, so this one's an addition. There we go. Right, so they just differ by one operation, okay? Using those, you can start taking our well-known angles like pi over 4 and splitting it in half, pi over 8. Using these, you can find both the sine and the cosine of pi over 8. Okay, wow, okay, nested radicals. Are you the type of person that thinks nested radicals kind of look cool? If you are, then maybe you would like to find the sine or cosine of half of that, which is pi over 16, or half of that, pi over 32, or et cetera, et cetera, et cetera, et cetera. So you can have nested radicals 3 or 4 deep. And those are exact values for sines and cosines of some now, maybe not well-known angles, but doable. So it depends on your aesthetic there, whether you think that's pretty or not, but it's kind of cool, in my opinion. Well, there you go. So I think we've gone through all the identities that you're going to need in the calculus. And now we just go on and use them in combination to get more and more identities. Why do we do all those identities? Usually just so that we can get through Calc 2 integration problem and make it into something simpler that is doable, right? So why you're going to want to know all these identities or be able to prove more identities is only going to become evident to you once you're in Calc 2. But that's why we're doing this in pre-Calc. All right.